Hi folks, this is Calc 3 Quiz 19. We're given a line integral and we're asked to evaluate it along two different curves C. So remember, the key to a line integral is you need everything in terms of one variable. So if you look at the line integral we're given, we've got x times z times ds, that's the arc length differential. And for part A, we're asked to evaluate this along the straight line segment between those points. So the first thing we need to do is find a parameterization for that line segment. And so how do we do that? Well, we starting at x equals 0, we're ending up at x equals -1. So it's 0 plus -1 minus 0t. That's where you start, plus the displacement times t. Now we go here for the y, starts at 2, and it doesn't change at all. Displacement 0. And then z starts at 1, and look at the displacement in the z direction. And this will be good for t between 0 and 1. So I simplify that. I get negative t 2 1 plus 3t for t between 0 and 1. So on this curve, let's go through and find the arc length differential ds. That's the magnitude of the derivative of r dt, which is the magnitude of the vector. Well, I take the derivative of this, -103 dt. You square the components, add them up, take the square root. I'm going to get 1 plus 0 plus 9, so I get square root 10 dt. So that's going to be the ds part. I look at the rest of my integral. I need to know what x and z are. I'm integrating on this curve C. The x is given by -t. So x of t on this curve is -t. Y of t, though we don't need it, is the constant 2. And z of t is 1 plus 3t. So when I go to substitute then on my line integral, the integral over C, xz ds, I just substitute each piece. I'm integrating over the curve C, but I'm going to change everything in terms of t. And the t runs from 0 to 1. So this is the integral from 0 to 1. X, which is -t, times z, 1 plus 3t, times ds, square root 10 dt. So just to make sure we all know what's going on here, that's the x on the curve, that's the z on the curve, and that's the ds. We just integrate this then using Calc 1. I can bring the square root of 10 out front. Integral from 0 to 1, multiply through -t minus 3t squared dt. So we bring that integral up then, and I get square root of 10, antiderivative -t, so -t squared over 2, antiderivative -3t squared, -t cubed. I'm evaluating this from t equals 0 to t equals 1. So what do I get? I get -1/2 minus 1, that's -3/2. I plug in t equals 0, I get nothing. So -3 square root 10 over 2. So that'll do it for part A. Okay, time for part B now. C is this helix. So here we're given the parameterization. And so we go through and find the ds. That's the magnitude of the derivative of r, just like it was in chapter 12. That's the magnitude of r prime. In this case, that's going to be 1. And then don't forget the chain rule here. It's -2 cosine. Don't forget the regular rules either. It's -2 sine 2t. And then 2 cosine 2t dt. And I square the components and add them up. And then the square root of 1 squared is 1, plus 4 sine squared 2t, plus 4 cosine squared 2t. That's all under the square root dt. And once again, we get Pythagorean magic happening here. You can imagine the kind of horrible terribleness we'd be in if we didn't have such Pythagorean magic. 4 sine squared of an angle plus 4 cosine squared of that same angle is going to be 4. So this just boils down to square root 5 dt. Now, on this curve, x is given by x of t is a function of t is equal to t. Y of t on this curve is cosine of 2t. And z of t on this curve is sine of 2t. So now I'm going to take this line integral and convert it into one variable. So I'm integrating over the curve C. I'm going to change everything as functions of t. The function of t here runs, it says, from 0 to pi. The x is t. The y, which we don't need, is cosine 2t. The z is what we need, sine of 2t. And then the ds is square root 5 dt. So once again, where's all this coming from? That's the x, that's the z, that's the ds. Alright, so it amounts to integrating this beast. So we can pull that radical 5 out, and we're left with integrating from 0 to pi t sine of 2t dt. Okay, so we've rewritten the integral here. To evaluate this, we're going to use parts. And so we would probably let u be the t and the dv be sine of 2t dt. So this is one of those examples where we can use the tabular method. And so I'm going to have a little table here for u and dv. So u I'm going to pick as t, and then I'm going to take derivatives of this until they zero out. Alright, so that's what we do here, is we take the derivative until it zeroes out. And then on the dv column, we put down the dv function, and then we integrate that thing until we get down to the bottom here. So don't forget the chain rule when you integrate. So we're going to pick up a negative 1/2, and then we're going to pick up another 1/2. And so just to make sure we all remember, here we're integrating with respect to t. Now we go through and match them up. We go diagonally down. We're going to multiply this by a +1, multiply this by a -1, and add up the terms. And let's see what we get. Well, we can't forget that square root 5. I get t times this times a +1, so negative 1/2 t cosine 2t, plus negative 1 times negative 1/4, that's positive 1/4 sine of 2t. This is being evaluated from t equals 0 to t equals pi. And let's see what we get. When you plug in the pi, you get negative 1/2 pi times the cosine of 2 pi. So I'm going to get a negative pi over 2 from this part. When I plug the pi into here, I'm going to get a 0. And when I plug 0 into this, I'm going to get a 0, and 0 into that, I get a 0. So the only thing I get in there is that negative pi over 2, but it's being multiplied by the square root of 5. So I get negative pi square root 5 over 2. That'll do it for part B, and that'll do it for quiz 19.